A single SQL query is just a tool, but a pipeline, well, a pipeline is a machine. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry ready and apply your knowledge to real industry projects.
I am really glad to be here for this one because that opening idea, the difference between just using a single tool
Yeah.
and actually building a functional machine, that is exactly the foundational concept we need to get into today.
Yeah, it really is. Today we are doing a deep dive into Lesson 8, which covers SQL for ML engineers. We're going to be looking at how to structure SQL logic, right? How to turn those really complex queries into robust data
Right,
pipelines.
which is a huge leap.
Exactly. And look, if you are listening to this right now, you probably already have a basic understanding of Python. You know how to write scripts, maybe define a few functions here and there. But today is really about building an intuitive mental model for machine learning engineering.
Yeah, we want to help you understand the architecture of data preparation um, before the data ever even touches a predictive model.
Right.
And we really need to establish why this matters for your career, too. Because this specific shift in thinking is the exact bridge between being a junior developer, someone who, just writes isolated queries to get a quick answer, and being a professional ML engineer.
A totally different lead.
Oh, absolutely. A professional ML engineer has to design maintainable, scalable data systems.
Hmm.
Operating at that enterprise level it requires an entirely different methodology.
Okay, let's unpack this because before you write a single line of code, you have to fundamentally change how you think about SQL. I mean, let's look back at the individual tools you've learned so far on this journey.
The core mechanics.
Right, the 6 core mechanics. You've got select, which is your projection tool for like picking the columns you want. You've got where for filtering data down. Join for combining different tables. Group PBY for aggregating data, finding totals or averages, things like that. Then case for transforming your categorical logic. And finally, window functions for that complex time intelligence.
Like calculating a running total over a 30-day period, right? Those are your fundamental building blocks. If
Yeah.
you know those, well, you basically know SQL syntax.
Exactly. But individually, they're just loose tools. It's kind of like having a bunch of loose Lego bricks scattered all over the floor. You have a red 2x4 brick here, a little blue square there, maybe a yellow wheel.
And they're useful.
Yeah, they're useful, but just sitting on the floor, they aren't doing much. If someone asks you a question, you might quickly snap two together, right? Like a select and a where,
Yeah,
just to see if a customer's payment went through.
right. A quick one-off task.
Exactly. But a pipeline is the fully assembled functional Lego factory line. It is a machine that takes raw plastic on one end, moves it through this series of like highly coordinated steps, and then outputs a finished boxed toy on the other end.
What's fascinating here is how that physical metaphor really translates directly to code. Instead of thinking, I need one query to give me one specific result right now, the ML engineer thinks input, transformation steps, output.
It's a completely different mindset.
It is.
Yeah.
You are building a machine because machines can be maintained, debugged, and scaled.
Yeah.
I mean, if you just have a giant pile of loose Legos and something goes wrong, you are basically blindly searching through a pile of plastic.
Oh, that sounds like a nightmare.
It is. But if a factory line breaks, you know exactly which station stopped working.
Right. So if we know we need an assembly line, what is the actual SQL mechanism we use to build it? Like, how do we stop writing these loose queries and actually start building the factory?
Well, we use what we can call the seventh SQL pattern, which is the pipeline pattern. And the way we physically structure SQL into these modular assembly line steps is by using CTEs, or common table expressions.
Common table expressions. Okay, let's break down the actual mechanics of that for someone who might be, visualizing this for the first time. A CTE is essentially a named intermediate result, right? The syntax usually starts with the word with. So you write with, and then you give your step a descriptive name, something like with actives arzers AS. And then in parentheses, you just write your standard select statement.
Exactly. And the absolute golden rule here, and you have to remember this, is that each CTE represents exactly one logical step in your pipeline.
Just one.
Just one. If we visualize the flow, it moves sequentially from top to bottom. You start with your raw data at the top. That flows down into step one, which might just be a filter to, remove deleted accounts.
Okay, so just filtering.
Right. Then that flows down into step two, which is an aggregate to calculate total purchases. Then down to step three, maybe a transform. And finally, it all drops down into your final output.
So is a CTE basically like setting up distinct workstations in a commercial kitchen?
Oh, I like that.
Yeah, like station 1 only chops the vegetables, station 2 only boils the pasta, station 3 only makes the sauce, and they just pass the ingredients down the line to each other until the final dish is plated.
That is a brilliant way to picture the isolation of tasks. And the reason we do it this way actually brings us to a core engineering philosophy, which is the single responsibility principle.
The single responsibility principle.
Right. Each CTE should do one thing and one thing only. If a CTE is filtering out users who haven't logged in recently, it should not also be trying to calculate their average purchase value.
Keep the chopper chopping and the boiler boiling.
Exactly.
But let me ask you this, kind of playing devil's advocate from a Python developer's perspective. Doesn't this just make my code unnecessarily long? I mean, if I break every single tiny operation into its own named CTE, aren't I just turning a 10-line query into a 50-line script?
I mean, yes, it does increase the line count. There is no getting around that.
Yeah.
But you have to realize we are trading brevity for readability and testability.
Okay, that's a fair trade.
To evolve your kitchen metaphor into a more technical analogy, think of a CTE like a variable or like a lazily evaluated function in Python.
Okay.
When you write a complex Python script, you don't cram all your logic into one massive, nested, completely unreadable line of code, have it?
No, of course not. That would be impossible to maintain.
Exactly. You assign intermediate steps to variables. You say clean data equals remove nulls from raw data, and then aggregated data equals calculate scenes from clean data.
Right.
Well, CTEs do the exact same thing for SQL. They define the logic step by step, but the database doesn't actually execute and, cook the data until the final select statement at the very bottom calls for it.
Oh, wow. Okay, that makes a ton of sense. It actually reads top to bottom like a script. And I imagine that makes debugging significantly easier.
Exponentially easier. By isolating responsibilities, every single step becomes completely independent and testable.
That's huge.
It is. Think about it. In a massive nested query, if the final output looks wrong, you have to mentally untangle everything to find the issue.
Yeah, which takes forever.
Right. But with CTEs, if the final table looks wrong, you just go to your editor, highlight the text, select star from step 2, and you just run that one chunk. You isolate the bug immediately.
You are checking the sauce station before the whole dish is ruined.
Exactly.
Okay, but wait. If my kitchen has 3 separate assembly lines going at once, say I've got one CTE calculating user profile data like age, another CTE calculating past 30-day transactions, and maybe a third looking at customer service tickets.
Very common scenario.
Right. How does the database actually put them on the same plate? Like, how do these separate parallel streams actually come together without accidentally mixing up customer A's data with customer B's data?
That requires a mechanism called feature convergence.
Feature convergence.
Right. Real ML pipelines are rarely just a single straight line. They're usually multiple parallel streams of logic. You might have CTEA, CTEB, and CDEC all processing totally different aspects of user behavior.
And eventually they have to merge.
Yes, eventually they have to merge. And we do this final feature assembly using vertical joins. Though in SQL syntax, we're typically executing horizontal joins, specifically left joins, to stitch these tables side by side based on a key.
So we're basically adding columns to a row, making the table wider and wider.
Precisely. In the final select statement, at the very bottom of your script, you use a series of left join operations. You take your master list of users and you left join the transaction CTE on the user ID.
Okay.
Then you left join the customer service CTE, again on the user ID. You use that primary key, the user ID, to essentially stitch all these parallel assembly lines together into one unified, very wide data set.
And that final wide data set has a very specific name in the machine learning world, right? It's called the feature matrix, usually just denoted as...
Yes, the feature matrix. The final output combines all of those engineered features into a very specific shape. It has to be one row per entity and many, many columns representing the features.
So you'd have a single row for like user 123 and the columns read, age 34, total spent $500, recent tickets to... activity score 8.5.
Exactly.
So what does this all mean? Like, why must everything converge into this really specific wide feature matrix shape at the end? Do ML models basically require this single unified snapshot of a user to make their predictions?
They absolutely do. That convergence is the exact handoff point to the machine learning model.
But wait, if I'm flattening everything into one giant row per user, aren't I losing all the granular detail?
What do you mean?
Well, if a user made 50 separate purchases over the last year, How does a flat feature matrix capture that nuance without turning into a 10,000 column nightmare of like purchase one, purchase two, purchase three?
Ah, that's a brilliant question, and it really hits on the exact purpose of feature engineering. You cannot just feed a machine learning model 50 raw transaction rows for one user and expect it to understand the user's overall behavior.
Right, it would just be noise to the model.
Exactly. You have to aggregate that granularity into meaningful summaries. You use your grouping and window functions, which we talked about earlier in the pipeline, to create features like total lifetime value, or average order value,
Oh, I see.
or even things like days since last purchase, or the standard deviation of purchase amounts. You are distilling their behavior into math.
So we are translating the total chaos of a relational database where data is scattered across dozens of tables and thousands of rows into this flat mathematical language that the ML model actually speaks.
Beautifully said. And that flat matrix is where SQL ends and the model begins.
Mm.
Because the machine learning algorithm, in its purest form, is just a mathematical function. It cannot rummage through a relational database.
It's not a detective.
No, it needs that clean, singular, flattened snapshot to learn patterns. The model looks at that single row and says, okay, when average order value is this and days since last purchase is this, the probability of them buying again is 85%.
Wow. So if you don't assemble the matrix properly using those joins, the model literally has nothing to learn from.
Nothing at all.
Here's where it gets really interesting, though. It's funny, when you first start out, you treat SQL kind of like a search bar, right? You just want to know if a specific thing happened.
Sure, just finding a needle in a haystack.
Yeah, but treating it like an automated factory line, that implies an entirely different level of engineering rigor. We have to start treating SQL with the exact same paranoia that we treat our Python scripts.
Paranoia is the perfect word for it. This is a massive psychological shift for a lot of data folks. We have to start viewing SQL as source code. Full stop.
Source code.
Yes, SQL pipelines are feature engineering code. They are not just queries anymore. They are the explicit logic that dictates what your artificial intelligence actually learns.
And if they are source code, that means we need version control. We need Git.
We absolutely need version control. Because if the data changes, the model changes. I mean, I have personally seen scenarios where a multi-million-dollar machine learning model predicting fraud in production suddenly just started blocking thousands of legitimate transactions out of nowhere.
Oh no, let me guess. Entire teams spent weeks debugging the complex neural network in Python, convinced the math was broken.
Exactly. Everyone thought the algorithm was failing.
But it wasn't the Python code, was it?
It wasn't the Python code. Someone had gone into the SQL pipeline, looked at a CTE that filtered transaction amounts, and accidentally changed a greater than sign to a greater than or equal to sign.
You're kidding. One character.
Just one character. That one tiny typo on like line 450 of a SQL script allowed a flood of $0 authorization pings into the feature matrix.
Oh, wow.
The model learned from that bad data, panicked, and just started flagging everything as fraud.
That is terrifying.
It is. If your SQL isn't treated like production code, peer-reviewed, tracked, and version control, your ML model is basically a ticking time bomb.
That perfectly illustrates why naming conventions and modularity matter so much. If someone writes a giant nested 500-line query without CTEs, you will literally never find that typo. But if you name your CTEs clearly, things like filtered valid orders, aggregated user history, final features, then anyone can read your code, audit it, and actually spot the anomaly. If you name your intermediate steps temp 1 or data 2, you are basically self-sabotaging.
Naming is communication. You are communicating your intent to the next engineer who has to maintain your pipeline.
Right.
But, we also need to be realistic here. Treating SQL like professional source code and heavily relying on CTEs means making some professional-level engineering trade-offs.
Let's talk about that, because the big trade-off we always hear about is readability versus performance.
Yes.
We just spent all this time saying CTEs make pipelines incredibly readable, modular, easy to debug. But wait, if we chain 10 or 15 massive CTEs together to process terabytes of data, doesn't the database just choke? Like, what happens to the system's memory?
That is the physical reality of the underlying hardware, unfortunately. To understand the bottleneck, you really have to understand how a SQL engine processes a CTE.
Okay, lay it on me.
When you run a query, the database engine, whether that's PostgreSQL, Snowflake, BigQuery, whatever, it tries to hold the intermediate results of those CTEs in its RAM.
In its active memory.
Right, it's active memory, so it can quickly pass them to the next step.
But RAM is limited.
Exactly. RAM is very fast, but it is limited. If your CTE is holding tens of millions of rows, the database will just run out of RAM.
And then what?
Well, when that happens, it has to temporarily write that data to the physical hard drive, which is a process called spilling to disk.
Uh-oh.
Yeah. Hard drives are vastly slower than RAM, so your query performance suddenly slows to an absolute crawl where the system just crashes entirely.
So what's the professional workaround then? If the pipeline is highly complex, processing massive amounts of data, and we know we're going to hit that memory wall, what do ML engineers do? Do we just abandon CTEs?
No, we don't abandon the pipeline pattern, but we do change the storage mechanism. In those really heavy-duty scenarios, engineers will use temporary tables or materialized tables instead of, or maybe alongside CTEs.
How do those solve the RAM problem?
Well, a temporary table explicitly tells the database, hey, don't try to juggle this in active memory. Write this intermediate step to the hard disk right now, and keep it there just for the duration of my session.
Oh, I see.
It takes a moment to write, sure, but then the database can efficiently query against it for the next step without having a memory panic.
And what about materialized tables?
A materialized table takes it a step further. It saves the result permanently to the disk, almost like taking a concrete snapshot of the data at that exact moment in time.
So as an ML engineer, you essentially have to weigh the cost of compute time, like how long the database takes to run the query and manage memory, against the cost of a human engineer's time trying to read and debug a messy query.
That is the eternal balancing act.
Yeah.
Usually, human time is vastly more expensive than compute time. So you default to readability. You use CTEs. You optimize for the human first.
Makes sense.
You really only sacrifice that readability or introduce the complexity of materialized tables when the compute cost or the execution time becomes a literal bottleneck for the business.
That makes perfect sense. But there is another strict requirement when we talk about treating SQL like code, right? And that is reproducibility.
If we connect this to the bigger picture, reproducibility is the absolute bedrock of trustworthy AI. In ML systems, there is a golden rule. The same input must yield the exact same output every single time.
Why is that rule so rigid, though?
Think about the life cycle of a model. An ML model is trained on historical data, right? Then it's validated on unseen past data, and then finally it's deployed to make predictions on live incoming production data.
The real-world stuff.
Exactly. Now, if your SQL pipeline calculates the total spent feature one way during training, say, it includes sales tax, but then it calculates it a slightly different way in production.
Like excluding sales tax because of some timestamp issue.
Exactly. If that happens, your model is completely blind. It is expecting apples, and you are feeding it oranges.
It's acting on fundamentally flawed premises.
Right. And the downstream effect of that is a model that makes wild, inaccurate predictions, not because the algorithm is bad, but because the feature definition literally shifted beneath it.
Wow.
The structured pipeline ensures the logic is locked in, version controlled, and identical across all environments. The pipeline is basically the guarantor of truth for the model. Without a reproducible pipeline, a machine learning model is worse than useless. It's actively misleading.
What an incredible journey this has been today. We started by looking at our scattered, loose Lego bricks, the 6 basic SQL patterns of projection, filtering, joining, aggregation, transformation, and window functions.
Yep, the basics.
And we learned how to snap them together using the pipeline pattern, leveraging CTEs to build modular top-to-bottom logic. We navigated the trade-offs of performance and memory, and finally, we saw how to use feature assembly to converge all those parallel lines into our final flattened feature matrix.
We moved from writing casual queries to architecting real engineering systems.
We really did. And now that we have these full feature pipelines and beautifully structured SQL systems, the obvious question is, what do we physically do with them? Which sets us up perfectly for our next step.
Yes, it does.
In Lecture 9, we are going to tackle exactly that. How do we actually connect this highly structured SQL database to Python? How do we ingest this feature matrix into our machine learning models to start making predictions?
That is where the actual artificial intelligence gets built, and it's incredibly exciting. But before we get there, I want to leave you with a final thought to mull over.
Oh, I love these. Let's hear it.
We talked about how pipelines completely control the data that feeds the model. And I shared that story about the tiny typo causing total chaos.
The greater than sign, right?
Right. Consider how changing just one small, seemingly insignificant upstream filtering rule in an early CTE, maybe changing a date range by a single day, or excluding a specific minor category of users, might invisibly, yet fundamentally, shift the entire behavior of the downstream ML model. It really makes you wonder how much power over artificial intelligence actually lies hidden in a simple SQL filter.
That is a powerful and slightly intimidating thought to end on. Treat your SQL with respect, version control your pipelines, and until next time, keep building.